Hello, so today we are going to do problems from Biweekly contest, this week's Biweekly 127. And the second problem is minimum levels to gain more points. So essentially we have possible array where we have values 0 and 1. 0 means that at that level, so it's a game with levels, and the value in the possible array at position I, if it's 0, that means whoever who plays that level gains -1 point. So they sort of lost and gain -1 point. And if it's 1, then that means they won and they gained 1 point. And we have this player, Daniel, Shang, DJ, and Bob. I don't know whether it's usually Alice and Bob, but this is fine. And so we have this as a player, and they play first and then Bob plays second. And you can think of them as they play continuous levels. So for example, let's say Daniel starts at first level and keep playing until some level J, and then at J+1 Bob starts playing until the end. And then this is what they say here, and then we want to the minimum number of levels Daniel here, who plays first, should play to gain more points than Bob, so to overall win more points than Bob. And let's consider both player will optimally play to maximize their points, okay? And so what we are looking to accomplish here is find the minimum number of levels that Daniel should play to gain more points. And if we can't, then we want to return -1, okay? And there is this caveat that is pretty important, is that each player must play at least one. So you can't have Daniel just play everything. Let's say if every level it was possible to get 1 point, you can't have Daniel play all of them. You have to have Bob at least play a level and Daniel at least play a level, okay? So that's the idea. You can take a look at the examples, but if you look at the possible array, it's 10 to the power of 5, so that rolls out any over squared solution. So let's see how we can tackle it. Okay, so how do we tackle this? Well, first thing to just get out of the way is, so the format that we get is like this, which is explicitly made to sort of slow you down. It's when the value is 0, we get -1 point. When the value is 1, it's 1 point. So let's just convert the array to that format. So if it's basically replace zeros with -1, okay? Once we do that, what are we really looking for? We are looking for the min number of levels such that for Daniel to play, let's just take a shortcut and call the first player Daniel. So the minimum number of level they can play to gain more points, basically, so that Daniel points, let's call them P for Daniel points, are bigger than the number of points that Bob gets. Okay, and remember the structure of the game is that, let's say Daniel plays with the color orange. Daniel plays all levels, so let's say this is level 1, level 2, level 3, and then all the way until some level. After that, Bob will play. So after that, we'll have, so let's say something like this. After that, it's, let's say Bob is green. It's Bob that will play all the way till the last one. Okay, so this is pretty important. Let's say this is some point I. Okay, and so what this means basically is that what we are looking for is some point here, the smallest point, because we want the minimum number. So the smallest point at which, the smallest I at which the number of points for Daniel is bigger than the number of points of Bob, right? And what is the number of points for Daniel? Well, the number of points for Daniel is just going to be the sum, right? So if they play this level, they get 1. If they play this level, -1. If they play this level, +1. If they get this level, plus -1, right? So what are we doing here? We are literally just accumulating the values, right? And so at this position, let's call it position I here, what is this? This is just the accumulation of the sum, right? So this is just accumulation of the sum up to I. And what is for this other part? What is the points for Bob? Well, the point for Bob is just the sum of the entire array minus the points for Daniel. Okay? So we are just looking for the point where the sum on the left side is bigger than the sum on the entire array minus the left side. So basically we are just looking for the point where the sum on the left side is bigger than the sum on the right side. And we want the first one because let's say at this point they can win, but if Daniel keeps playing until let's say maybe J, they will win as well. Well, we want the minimum number of levels. The number of levels here is I, so we can just play this and he doesn't need to play the other levels because we only want the minimum number of levels, right? And so that's pretty much the approach we can take, where we can keep track of the sum of the left side and the sum of the right side. And the first point where if this is, we can just go through the indices, and the first point where the sum for the left is bigger than the sum for the right, we just return that. We'd have to take care of indices because with the arrays in Python or in the language you are using, it starts with 0, so we will need to take care of making sure we return I plus 1, just because if, let's say, Daniel plays only the first position, then we want to return 0 plus 1, right? So that's just small indices change. But in terms of the sums, how do we keep track of them? Well, left will start out as 0. And then for the right side, well, it can just start at the sum of the entire array of, let's call this P. Let's call this array P. So it can be just the sum of the entire array, so P here. And then as we go for each I, what we can do is we can just for left. Each time we move a position, that means Daniel will play this level. If we move in this one, if we move here, that means Daniel will play this one. And so each time we move, we will add the level Daniel plays. And since right, we started out as the sum of the entire array, whatever Daniel played, we need to subtract it because it's no longer part of the right side. And so we need to do minus pi. And we do this check afterwards. And that's pretty much it. So pretty straightforward once you figure out how to do the setup for the prefix sums here. Yeah, that's pretty much it. Let's code it up and make sure it passes. Okay, so how can we code that up? So first we need just to get the length so we can use it. And then we just need to do what I mentioned, which is basically mapping zeros to -1. And let's call this x. And 1, just keep it as 1. Okay, so that's the first step. Now we can just keep track of left and right. We said initially left will just start with 0, and right will start with the sum of the entire possible thing. And then we'll reduce from the left and we will add to the left and reduce from the right. Why are we doing this? Because we want the first smallest I. That's why we are starting with left equal to 0, because we want the smallest I where left is bigger than right. Okay, and so that's what we do here. We get the range for n. We want to stop at -1 because we want, so this means in Python that -2 would be the last thing we process. Now remember, each position I means basically, in this case means Daniel will play level I, right? And so if we go all the way until n, that means Daniel can play level n-1. And that would mean there will be no level left for Bob. And that violates this condition, which says that each player must play at least 1 level. So we have to leave at least the last level to Bob. And so that's why we stop at n-2 so that we leave n-1 for Bob, no matter what, okay? Okay, so that's the idea here. Now what do? We get, for right, we need to subtract the current level, basically point. And then for left, we want to add it. And if the first one where left is bigger than right, that means the number of points for Daniel is bigger than the number of points for Bob. We should return I plus 1. Now, why I said I plus 1? Why? Because here we start indexing from 0, but the levels are counted from 1, so we just account for that here. Now, if we exit and we didn't find any point where the number of points for Daniel is bigger than the number of points of Bob, then that means there is no way Daniel can win, and so in that case, we return -1. So we return -1, and that's pretty much it. Now let's run this. And let's submit. Okay, so that passes. Now in terms of time complexity, this is all event time here, because we're just doing one loop. And then relatively, you can argue that it's constant space, but then again, we just replaced this possible array. We could also just do something like this to make it easier, and then just replace these values here. It's debatable whether that would be considered O(n) or O(1). I would say it can be considered O(1), but yeah, it's not a lot of extra space anyway. Yeah, so that's pretty much it for this problem. Thanks for watching, and stay tuned for the other weekly contest videos. Thanks for watching. See you in the next one. Bye.